Okay, so we have our document open for H5 here, and this is the initial circuit that I designed for this problem. I had to choose an input frequency to make the impedance of the inductor the same magnitude as the impedance of the resistors. So I first had to calculate the impedances, and I ended up choosing a frequency of 1 kilohertz. I used the equations found in the notes to calculate for the average, reactive, and apparent power, as well as the RMS, current and voltage. I then had to solve for the required capacitance to correct the power factor. I used the equation of the combined impedances of the capacitor in parallel with the load network and rearranged to solve for the capacitance required. I then measured the actual values of the capacitors that I had to redefine the problem circuit. I also had to rearrange the equation that I used to find the mystery capacitance to solve for the new frequency that I would use to accompany for the imperfect value of the capacitors. This was the new circuit that I designed in Multisim with the new capacitance and new frequency. These are the displays of the oscilloscopes in Multisim before and after the power factor correction, and this is the display with the time cursors. I used the time difference between the peaks of the voltages to solve for the angle, power factor, and power. Alright, so we have our physical build of the circuit for H5 here. As you can see, we have 2 oscilloscope probes hooked up to the circuit, as well as the waveform generator. So we have our channel 1, which is right here, this black oscilloscope probe, and it is hooked up in series after the input of the waveform generator, to this blue wire, and then that is in series before the inductor, and it's shown in a similar way here. So we have our oscilloscope, this is channel 1, and it's hooked up in series after the input and before the inductor here. Alright, let's see, channel 2 is connected here, it's this gray one, and we can see that it is hooked up right before R3, and on the Multisim diagram, it is also hooked up right before R3. Alright, and both of these share a common ground, which is just connected right after R3. And we can see that here, the ground going to the oscilloscope probe. Then we have our red waveform generator input, and it's going to this bottom rail here, supplying power to the circuit. And then we also have our ground here, which is this negative rail, which is providing the ground for the circuit. Alright, so we have our hand tech over here, and this is the waveform generator menu, and we have our frequency at 984, which is the one that I specified in the lab report, which was redefined when I had to reformulate the problem to accompany the physical values for the capacitors that I actually had. So we have our frequency at 984 Hertz, we have our amplitude at 1 volt, and we can just press play on this, so this will provide power to the circuit. And then we can go over to our scope probes, and as we can see, the voltages, the yellow one is the voltage being supplied by the input, and then the green one is the voltage that is after the load network. So we can see that the voltage, the green voltage across the load network is actually lagging the voltage supplied by the waveform generator. And we know that because it's an inductive load. So right now, the phase is a little bit off. As you can see, they're not totally in phase. So let's see what happens. I'm going to plug this white wire in here with these capacitors in parallel, and we're going to see what happens. I'm going to try to hold my camera up there. Okay, so before power factor correction and after power factor correction. So you can see the voltages are more or less in phase. They're a little bit off, and that's just due to error in the physical build, setting it up, measuring the values for all the components. But as we can see, it does a pretty decent job. So that is the physical build.